Welcome to a deep dive into the very language of uncertainty, probability. In the world of machine learning, we constantly deal with data that's messy, unpredictable, and often incomplete. Understanding probability isn't just a mathematical exercise, it's fundamental to building robust, intelligent systems that can make sense of this inherent variability. Today, we'll demystify core probability concepts and see how they form the bedrock of many ML algorithms. At its core, probability is simply the measure of the likelihood of an event occurring. It's expressed as a number between 0 and 1, where 0 means the event is impossible and 1 means it's certain. Think of it as quantifying our belief or expectation about a future outcome. Whether we're predicting stock prices, classifying emails as spam, or diagnosing diseases, we're constantly working with probabilities. Our journey begins with the concept of a sample space. This is the set of all possible outcomes of a random experiment. For instance, if you flip a coin, the sample space is heads, tails. If you roll a standard 6-sided die, the sample space is 1, 2, 3, 4, 5, 6. It encompasses every single result that could possibly happen, providing the complete context for our analysis. Building on the sample space, an event is any subset of that sample space. It's a specific outcome, or a collection of outcomes that we're interested in. Using our die roll example, an event could be rolling an even number, which would be the set 2, 4, 6. Another event could be rolling a 3, which is just the set 3. Events are what we assign probabilities to. Calculating basic probabilities is straightforward once you have your sample space and event defined. If all outcomes in the sample space are equally likely, the probability of an event A is the number of outcomes favorable to A divided by the total number of outcomes in the sample space. For example, the probability of rolling an even number on a die is 3 divided by 6, giving us 0.5. Now let's introduce conditional probability. This is where things get interesting and incredibly relevant for machine learning. Conditional probability is the probability of an event occurring, given that another event has already occurred. It changes our sample space. For instance, what's the probability of rolling a 6 on a die, given that you know an even number was rolled? Our context, our sample space, has shrunk. The formula for conditional probability is often written as P, which reads the probability of A given B. It's calculated as P/P. In our die example, P means we are looking for the probability of rolling a 6 and an even number divided by the probability of rolling an even number. Contrast this with independent events. Two events are independent if the occurrence of one does not affect the probability of the other occurring. A classic example is flipping a coin twice. The outcome of your first flip has absolutely no bearing on the outcome of your second flip. P would simply be equal to P if A and B are independent. The distinction between conditional and independent events is crucial. If knowing B tells you something new about A, they are dependent, and we use conditional probability. If knowing B provides no new information about A, they are independent. In ML, features in a dataset are often assumed to be independent to simplify models, but in reality, they are usually conditionally dependent on other factors or the target variable itself. This brings us to one of the most powerful concepts in probability, especially for machine learning, Bayes' Theorem. Intuitively, Bayes' Theorem helps us update our beliefs about an event based on new evidence. It's about reversing conditional probabilities. Instead of asking P, it helps us calculate P, which is often what we truly want to know. The theorem states P equals /P. Here, P is our prior belief in hypothesis A before seeing any evidence. P is the likelihood of observing evidence B if hypothesis A is true. P is the total probability of observing evidence B. And P is our posterior belief in hypothesis A after considering evidence B. The relevance of Bayes' theorem in machine learning is profound. It's the backbone of algorithms that learn from data and make predictions by updating probabilities. It allows models to incorporate prior knowledge and adjust their predictions as more data becomes available, making them robust and adaptive. From spam filtering to medical diagnosis, Bayes' theorem provides a principled way to reason under uncertainty. Perhaps the most famous direct application in ML is the naive Bayes classifier. This algorithm, despite its naive assumption of feature independence, is surprisingly effective for many classification tasks, particularly in natural language processing like sentiment analysis or document classification. It leverages Bayes' theorem to calculate the probability of a data point belonging to a certain class, given its features. In conclusion, probability is more than just a mathematical abstraction. It is the fundamental language we use to understand, quantify, and manage uncertainty in the real world and in our machine learning models. From basic events and sample spaces to the powerful insights of conditional probability and Bayes' theorem, mastering these essentials equips you to build more intelligent, resilient, and accurate AI systems.